this class. Okay, class is being recorded now. And anyone is ready can go ahead, present.
Can you see my screen?
Okay. Yes, go ahead. Oops. Zakia.
Sorry, yeah, I already shared. That's okay, you can go ahead. Let me stop
I
sharing.
can do next. Oh.
Go ahead, you can do it.
Can you see my screen?
I think it's popping up. Yes.
Can you see it?
Yeah.
Okay, this is question 64. While driving along a long route that has 5,000 intersections, the probability of encountering a red light at any intersection is 0.001. Find an approximation for the probability that a driver will encounter at least 2 red lights. So let x be the number the driver encounter at red lights. We're looking for when it encounter at least 2 red lights. That means we're looking for when x is greater than or equal to 2. And we also know the component of x equal O. When the component of x greater than or equal to 2 is that when x equal to 0 or x equal to 1. And for here, we know the probability encountering at a red light is 0.001. That means no matter which intersection, the probability will be always 0.001. That means the average probability of x is 0.001. So we have, that's what we got. And then we just calculate the average number by 0.001 times 5,000 because there's 5,000 intersection total. And we got our average number. That would be the expected value, lambda. And then since this is, since we have lambda, we can use the Poisson random variable. And then we just plug into the formula. We got this. That's the component of when x is greater than or equal to 2. And then we just subtract. So we just want to subtract this. We got our final answer.
Wow. 96%.
90, yeah.
That's 5,000 because that's 5,000. I like this question because this combined with binomial random binomial distribution and the Poisson distribution. So you have to get the lambda from binomial distribution. So that's why you have a probability multiplied by n trials, 5,000, right? You get 5.
Yeah.
Okay, great. Yeah, that's the expected value. Great, then use Poisson probability distribution. Nice. Next one.
Hi, Professor.
Yes, okay.
You can see my screen, right? Yes?
Yes, I guess you are at work.
Okay. Oh, okay. So I'm presenting question 82. Suppose that a class of 50 students has appeared for a test. 41 students have passed this test, while the remaining 9 students have failed. Find the probability that in a group of 10 students selected at random, none have failed the test, and B is at least 3 students have failed the test. So number of total students is 50, and I I just let X be the number of failed students. So the probability of failed students is 9 over 50. Um, as it is given, 9 students have failed the test from 50. So 9 out of 9 over 50, 0.18. And we have to find probability for a group of 10 students. So here we're gonna use the binomial random variable formula where we have n equals 10. And then so question A asks that we have to find none probability that none have failed the test. So it's gonna be x equals to 0. So here's the formula: 10 choose 0, and the p we have 0.818 to the power 0, multiply 1 minus 0.18, which is the 1 minus p from the formula, and to the power 10 minus 0, and the answer is 0.1374. And question B, they say at least 3 students have failed the test. So probability x is greater than or equals to 3. So we can this equals to 1 minus probability of x is smaller than or equals to 2. So we can find 1 minus the summation of the formula. So where we gonna choose x0 to 2. We're gonna find from x0 to 2. Yeah, and then 1 minus 1. So yeah, so n is 10 over here, and x we're gonna put 0 for first time, and then we're gonna add 1 and then 2, and the probability is 0.18. And yeah, so I just skip that part. So we have to do when it is 0, we have to put x equals to 0, and then we have to put x equals to 1, and it's gonna be x equals to 2. We add all these terms. And for x equals to 0, we already know, we don't have to solve that again. We already know that is 0.1374. We have to find for x equals to 1 and then 2. We have to add them. The answer is 0.7372. We're just gonna subtract that from 1. The answer is 0.2628.
Great.
Yeah.
Nice. Thank you, Zakia.
Thank you.
Probably not on this exam. Probably, Catherine, yes. Because the first exam will cover the first 4 chapters, but they're all very basic from the later ones. All right, next one. Yeah, basic ones are tricky, huh? What do we call basic ones? Basically, no surprise. If you understand the examples I have been talking in class, and you guys have done many different types of homeworks, you know, so it should be fine. 12 questions on the test. Okay, next one. We still have a Hall, Kara, Shuyin, Yinping. Okay, how is coming?
For question 4.86, you need to go to this proof to know that the E of x is equal to lambda. Then
What is the question?
this 4.86.
Right, let's read the question first, so
A
we know what to do.
neighborhood consists of 5 streets. Assume that the numbers of daily traffic accidents that occurs on these streets are Poisson random variables with representative parameters 0.45, 0.2, 0.4, 0.5, and 0.35. What is the accepted number of traffic accidents that will occurs in this neighborhood next Monday.
Mm-hmm.
And this one shows that the accepted value is equal to lambda. And then I just like add the numbers of the Poisson random variables have occurred in the daily traffic to get the accepted numbers of the traffic accident that will happen on Monday.
Hold on, let me think. So, okay. So the expected value for Poisson is a number. And the values of Poisson, the probability, hold on. Assume that the numbers of daily traffic accidents that occur on these streets are Poisson with respective parameters. 0.45. Okay, what are those numbers? What does
Those
this mean?
numbers were the daily traffic accident occurred on the street.
0.45, 0.2,
Yep.
0.4, 0.5, and 0.35. Okay, then you will see add up all those values. 1.9. What's that?
That's
That's
this one
expected number of traffic accidents that will occur in this neighborhood next Monday.
Since it's like the daily traffic accident, so it happens every daily, I guess.
So that's your number, right? 1.9
Yeah.
is your number. Oh, okay, I get that. Okay, I see. All right, thank you. If anyone has any questions, feel free to jump in.
Hi, Professor. Good evening.
Yes, Kara.
I am going next, Professor.
Okay.
Can you see my screen?
Popping up. Yeah.
Okay.
It's here now.
I'm going to present question number 71 of chapter 4. In response to an attack of 10 missiles, 500 anti-ballistic missiles are launched. The missile targets of the anti-ballistic missiles are independent, and each anti-ballistic missile is equally likely to go towards any of the target missiles. If each anti-ballistic missile independently hits its target with probability 0.1, use the Poisson paradigm to approximate the probability that all missiles are hit. So, from the information observed that in response to an attack of 10 missiles, 500 anti-ballistic missiles are launched. The missile targets of the anti-ballistic missiles are independent, and each anti-ballistic missile is equally likely to go towards any of the target missiles. Choose some missile out of 10 of them and consider the probability that some anti-ballistic missile hits it. First of all, probability that some anti-ballistic missile chooses that fixed missile as its target is 0.1, since it chooses randomly. Also, if that was the case, the probability that it has been hit by the anti-ballistic missile is 0.1. Thus the probability that some anti-ballistic missile will hit our missile is 0.01. Consider x is the random variable that represents the number of anti-ballistic missiles that have hit on fixed missile. Therefore, x follows Poisson, distribution with parameter lambda, which is equal to 500 multiply 0.01, which is equal to 5. Probability that our missile has been hit, probability of x greater than equal to 1, which is equal to the complement 1 minus probability of x less than 1, and from the Poisson distribution we will get probability into x is equal to 1. So when we expand it, we will get 1 minus e to the raised to the power minus lambda, and lambda raised to the power 0 over 0 factorial. Substitute value of lambda is equal to 5. So after the solving it, we will get 1 minus exponent raised to the power of minus 5. So when we solve it, we will get 0.9933. Probability that all of the missile have been hit. So we have to raise to the power of 10 of this answer, and we will get that 0.9346 or 93%.
Wow, pretty high. Okay, very clear. Thank you.
Thank you.
You guys are teaching me. Thank you.
Good evening, Professor.
Good evening, Shoyun.
Can you see my screen?
Yeah.
Okay, so I'm going to present question number 55 on chapter 4. So the question is, the monthly worldwide average number of airplane crashes of commercial airlines is 3.5. What is the probability that there will be A, at least 2 such accidents in the next month? So in this question, we use the Poisson distribution. And by the question, we know that the lambda is 3.5, and x here is the number of accidents. So at least 2 accidents is also means 2 or more accidents. So the probability of x greater and equal to 2 is equal to 1 minus the probability of x less than 2. So x less than 2 is also x equal to 1 and the x equal to 0. So it's 1 minus the probability of x equal to 1 plus the probability of x equal to 0. So we just plug in all the numbers into the Poisson distribution, and we will get the answer is 0.864. And B, at most 1 accident in the next month. So at most 1 accident is also means 1 or 0 or 1 accident. So the probability of x less than equal to 1 is equal to the probability of x equal to 2, x equal to 0 plus x probability of x equal to 1. And also plug in the number, we will get the answer is equal to 0.1359.
Nice. All right. Good. Good job.
Excuse me. Can you see my screen?
Yeah.
My
This is
question is 66. Customers enter a supermarket located on a busy street at a rate of 2 every 3 minutes. And for question A, what's the probability that the customer enters the supermarket between 7 a.m. to 7:06? So we use the formula, the Poisson formula. We have the lambda is equal n times p. The n is the rate of customers enter is 2/3, and the p is the time usage. In this question is 6, so the lambda is 4, and for the I is the number of customers enter. So for question A, we found the no customer, so it's p x equal to 0 equal to e to the negative 4 power times 4 to the 0 power over 0 fraction. So the answer is 0.0183. And for question B, what's the probability that at least 5 customers enter during this time? So we calculate the customers from 0, 1, 2, 3, and 4. We want to have the x greater or equal to 5. It's 1 minus p x less than 5. So the final answer is 0.5 37114.
Great. Nice. Nice. In 6 minutes, 4 customers logged in. All right. That's 音频. Okay, did everyone go? Yes. Anybody else like to present? Sure, Tom. Let me make a presenter. Any other ones, especially those of you who haven't been presenting? It's an easy way to earn your grades. Because you have to do the homework anyway. Okay, Yongxin. All right, let me make you a presenter. You have to do the homework anyway. Why not pick up one from your homework to tell us? Tom, when you get home, professor will be teaching class. Catherine, what is that? Oh, Tom, when I present, or can I present when I get to my home? My market, my armchair got stuck. Oh, I see, Tom. That's okay. Well, you can present next time. I didn't read the whole thing. All right, so that's Yongxin then. Yongxin, your turn to present.
I wanted to present question 37.
Okay.
It's the file is converting.
Okay.
Okay.
All right. Anyone else like to present? Choose one out of your homework, especially for those of you who don't really have much credits from presentation. The presentation, Jie has the highest one. He did it 13 times, which is 130 out of 100. Okay, go ahead. Oh, we haven't seen your file yet.
37. Consider problem 4.22 with I equal 2. Find the variance of the number of games played and show that this number is maximized when p equals 1/2. So, I screenshotted the question 22, and then so the variance of x is p of x equals 2 times p of x equals 3, which is 2p parentheses 1 minus p times p squared plus parentheses 1 minus p squared. And then if you plug this equation into the calculator, you get that it's maximized at 1/2.
Yongxin, you finished?
Yeah.
Oh, we lost your voice.
Yeah.
Oh, I was looking at this. You have A. I see you have A. There's no B part, right? Just A.
Yeah, just this one question. Simple.
Oh, I see.
Yeah.
So your answer in the end is negative 2p squared plus 2p?
Yeah, I just simplified it.
Okay. I see. Oops. All right. Okay, that's Yongxin. All right. Thank you, Yongxin.
Thank you.
Yongxin. Trying to give you credits. Yeah, that was fast. Because part of the answer is from 22, question 22. Okay. All right. Anyone else like to present? you can change your mind while I was talking, and today's class will be, what I was going to be talking shouldn't be long. What's going on? Okay, it doesn't share. Let me redo this. So the last one to talk about in chapter 4 is geometric random variable. So we're not going to talk about negative binomial random variable and hypergeometric or zeta. So we're going to finish at the geometric random variable.
Professor, I got a question.
Yes.
Like, can you get like a sheet for the formulas for like the random variables? Are you allowed to have it on the exam?
Oh, okay. You mean the formulas for each distribution?
Yep.
Oh, I see. You know what? Good news for you. The exam will be open book. All right. You just cannot consult with websites, because I know the websites has something like, can you help me with the questions like that? But you can create a cheat sheet, or you can consult with your homework. All right. Because 12 questions, it's for probability class, it's quite a lot. And so that's my answer to you. Yeah, basically it's an open book. You just cannot consult with anybody else or with the internet. You can consult with the things you have on your own. Final will be different because the final will be in person. And final you could have a formula sheet, right? It won't be open book, but for the midterm it's open book, okay? And also remember, presentation will add to your final grades. Okay, any other questions? What if we are from a different college? What do you mean by that? The final will still be on campus though.
I'm from New York, so would I easily have access to the Brooklyn campus?
Okay.
You
But
just have to show the pass for like the COVID. You can go in.
Oh, Catherine, your question is how to get onto how to get into the campus, right?
Yeah.
Oh, since you registered for the class, you should be able to get a student ID. There's something called Brooklyn Navigate. Brooklyn College Navigate.
Okay, I'll look into it. Thank you.
Okay, I'm just checking for you to see what is called. Yeah, it's called BC Navigator. You just have to get that app to run on your cell phone. It will show you're registered for the class, stuff like that. Okay. Oh, clear 4. I have no, oh, clear 4. Okay. There's something else. Okay, so to cover the syllabus, right, we talk about geometric random variable. This also should be easy because Poisson distribution.
Professor?
Yeah.
Tom is going to present.
Oh, okay, Tom. You made it.
Okay. So for this question, we are given n trials with respective probabilities of P1 to Pk, and pi is small, we're given the problem where no outcome occurs more than once is approximately equal to e to the minus n times n minus 1 some pi squared over 2. So the first step is thinking of it as like selecting a unique number on like natural numbers. And since p is small, we can deduce that we should use a Poisson distribution. And then the formula is given as lambda I e to the minus lambda over I factorial. So for the possibilities of n, basically use the fact that 1 plus 2 plus ... n is equal to n times n minus 1 over 2. And p is equal to pi squared. And then once we plug that into the Poisson, where I is equal to 0 for 0 same outcomes, we get the results.
So it's e to the negative, but so in the question, lambda is given, right? Lambda is given as e to the...
Lambda is the mean.
It's
so lambda is
e...
n times p.
Hold on a second. Oh, okay. So the probability, right? Those are the probability of e to the negative and blah, blah, blah.
So like the main difficulty is showing that the term in lambda is n times n plus 1 over 2, which is from, like, say you're picking a number from 1 to n. The possibilities is n times n plus 1 over 2, because
that's
every
when
time
you add
pick
1 to n.
Every time you pick an n value, you have to you have n minus 1 possibilities, and we repeat this until we get to 1. So it's kind of like 1 plus 2 plus to n.
I see. Okay, thank you. You always pick the next questions to show, challenging ones to show. Okay, that's Tom. Tom also reached 110. All right. Thank you, Tom. Okay, so geometric random variables. So remember, a binomial, we have nice formula for expected value and variance. And Poisson distribution, we have a nice formula for expected value and variance. Similarly, for geometric random variables or geometric distribution. I'll read. Suppose that independent trials, each having a probability of p in between 0 and 1, not to be 0, not to be 1, of being a success, are performed until a success occurs. If we let x equal the number of trials required, then p of x equals n, so it means this until the nth trial success appear, equals to the probability of the failure, n minus 1 failures, then finally 1 success. So p raised by 1. So nice Nice formula. I think last class someone already used this. Choose the problem from chapter 4 already applied this, but he just didn't mention this is geometric distribution. So this equation, because in order for x to equal to n, it is necessary and sufficient that the first n minus 1 trials are failures and the nth trial is a success. Since the outcomes of successive trials are assumed to be independent, and we can calculate this because we have, like, you know, who knows, infinite many trials. So n goes from 1 up to infinity, and success happens at the nth adds up to be probability. So this p, so adds up all those probabilities for from the first trial, from n equals to 1. And what is this? We recognize 1 minus p is less than 1. Geometric series, right? Anybody recognize this? This is a geometric series. So we can use the formula of geometric series, which is the first term will be p, because when n equals to 1, 1 minus 1 will be 0, right? So p is the first term. And divided by 1 minus the ratio r. The ratio r is 1 minus p. So p over p, that equals to 1. So it is a probability distribution. Because whenever we want to see something, it is a probability distribution. It has to meet the 3 axioms, right? Each probability has to be in between 0 and 1, and can be 0 and can be 1. And also has to add up all the probability of the outcomes adds up to be 1. What else here? It follows that probability is 1, success will eventually occur. Any random variable x with probability mass function given by this is said to be a geometric random variable with parameter p. All right. Let's example 8. An urn contains n white and n black balls. Balls are randomly selected one at a time until black one is obtained. So I have n white and black. And if we assume a black one is obtained, if we assume that each ball selected is replaced before the next one is drawn, what is the probability A, exact n draws are needed, B, at least k draws are needed? Okay. Remember, this is replaced. So if we let x denote the number of draws needed to select a black ball, that's our goal, then x satisfies the equation, this formula, 1 minus p raised by n minus 1 failures and n trials to be success. So with p, what is the probability? We have m black ones. Totally, we have n plus m ones. So the probability of getting a black one is out of n is n divided by n. No, it's m divided by p equals to m divided by m plus n. And 1 minus p, so this is our probability p. And 1 minus this should be this. 1 minus this should be this. So let's see. 1 minus this. 1 is m plus n divided by m plus n. M plus n minus m, indeed, is n over m plus n. So this is 1 minus. So this is failure. 1 minus this. Right? So we have n minus 1 failures. And finally, we reach nth one to be success. And we simplify this, we get this. So that's the first one. B, at least k draws are needed. So that means our random variable has to be greater than or equal to k. So we start from n equals to k until infinity, and we also have this, right? Sum up all those failures, n-1 failures, and reach the n's to be success. And to calculate this, again, this is less than 1. Again, we have a geometric series, right? So just use the to calculate the geometric series. Then do the calculation in oh no, hold on. This is n equals to k. This is n equals to k. So what do we do? So this is k minus 1. Oh, that's okay, right? Because n start with k. So the first term is still this. And then first term is, what's the first term? First term is k minus 1 of this times this, right? That's our first term. Then divided by 1 minus r. 1 minus r. This is our ratio in geometric series. So 1 minus this, that's just this. That's just this. So those two are simplified. One in the numerator, one in the denominator. Those two are simplified. So end up with this failure raised by k minus 1. Interesting, huh? At least the k draws are needed. So for a geometric random variable, probability of x greater than or equal to k, so we have from here, is 1 minus p or raised by k minus 1. So this is another great formula to use. Okay, now let's calculate expected value of a geometric random variable. So Q equals 1 minus P. And expected value equals to the random variable values multiplied by its probability by geometric random variable is 1 minus P, which is Q raised by I minus 1, then multiplied by P. Well, we can do a little bit of trick. So we do I minus 1 plus 1. Minus 1 plus 1 is 0. We can always additive inverse. We can always add 0 to anything. Then we split. We split it to be I minus 1 of this. Because now we have I minus 1 and Q raised by I minus 1. And then this 1, so 1 multiplied by this. Well, what is this? This is just 1, right? This is a whole thing, all the probabilities for the geometric distribution. So that just adds up to be 1. So this part is 1. But what about this part? This part is I starts from 1, but this is I minus 1. Maybe you want to reindex. If we reindex with j equals 0, which means I equals to j plus 1. So I equals j plus 1, then I minus 1 is j. So I minus 1 becomes j. Now we have j starts from 0. We have the j q raised by j p. Well, then we reindex. We reindex again. Let's see what happens. So now j starts from 1. So basically we leave out one term because j equals 0. Well, 0 times anything will be 0. So this one equals to this one, right? Because the first term is just 0. 0 times anything will be 0. So then we'll start with the second term. The second term is j, but j minus 1. Right? We start with j equals 1. J equals 1. J equals 1. But q start with 0, right? Q raised by j, q raised by 0. So we have to justify this. So this j now becomes j minus 1, right? Because the exponent of j starts with almost 0. So then what is this? So this is the expected value of the geometric random variable, right? So what do we get? We get an expected value of geometric random variable equals 1 plus q of this. Well, if we move this one to the other side, factor out e of x, so we have 1 minus q, which is p. So that means p times e to the x equals to 1. So that means expected value equals to 1 over p. Fantastic. Fantastic. Okay. So in other words, if independent trials are having a common probability p of being successful are performed until the first success occurs, then the expected number of required trials equals to 1 over p. For instance, the expected number of rows of a fair die that it takes to obtain the value 1 is 6, right? Because it's 1 over 6, then 1 over 6 is 6. Anyone has any questions? That's right, Ayat, yes. That's right. Okay, let's calculate the variance of geometric random variable. Because all those binomial, Poisson, geometric, and then later on I have some others, they have formulas. So in life, we just need to know when to apply these formulas. All right, let's see how to calculate the variance of a geometric random variable. So remember, we have the formula, variance of x equals to expected value of the random variable squared minus expected value being squared. So we use the formula. Expected value squared equals 1 over p squared. Expected value of random variable squared, so we have this. We have I squared, do this. Then we do the same trick. Then we have this I minus 1 squared. And what is this I minus 1 squared? And here we have this. Excuse me. Those calculations are interesting. Huh? So the last one is 1 is easy. And this one, if we factor it out, if we expand it out, we have I squared minus 2i plus 1. So we have minus 2i. Then here we have plus 2i. So that should go out. So we have I squared. Then we have plus 1. Then here we have negative 2. Plus 1, negative 2. 2i, negative 2i and 2i cancel out. We have a plus 1 from here. We have negative 2 from here. But I don't see here. Here we have plus 2. What happened? So let's see. This reindexed. So I squared, I being reindexed to j start from 0. Oh, this is okay, right? We can even write I equals 0. Why? Because 0 squared would be 0. 0 times anything would be 0. That's 0 term. Basically, we just ignore the 0. We just add 1 0 term. But to do this, because I equals j plus 1, so I minus 1 becomes j. I minus 1 squared becomes j squared. Then I minus 1 becomes j. right? So what is this? This is J squared QJ P. So we need a QJ minus 1. So we factor out 1Q. Then J squared Q to the power J minus 1 times P. That would be expected value of random variable squared. Maybe this one, right? Multiplied by Q. Then this one, what do we have? We have J times Q raised by J. Well, we split Q as Q times Q J minus 1. Because Q J minus 1 times P with all this summation, that's just expected value times Q, then plus 1. All right. So we have Q, this one, we have this one, we have these 3 terms. Now minus 1 minus P squared. What do we have? We have this. We have expected value of the random variable square minus Q, so that becomes a P, expected value of the random variable square, equals to this, P 2Q, expected value of X plus 1. We have this, right? And expected value is 1 over P. So we get this. We get the P times expected value of the random variable square equal to 2Q over P plus 1. Now we do, so what do we do here? Expected value. Now we divide by P on both sides to get this, right? Combine those two, divide by P, so get this. Simplify a little bit, because Q is 1 minus P, you know, so, or P is 1 minus Q, so get this. Then we subtract by 1 minus P squared. Nice formula for geometric series, geometric distribution. The variance of geometric random variable is 1 minus P over P squared, right? Expected value of geometric random variable is 1 over P. And the variance is 1 minus P over P squared. Very nice, huh? Very nice. So in life, it's all about to figure out a situation, you know, fits into which probability distributions, then to apply the probability distribution. Negative, let me see. I don't think negative binomial is covered in our syllabus. Let me just double check. Yeah, Bernoulli, binomial, Poisson, geometric. Oh, yes, it is negative binomial random variables. Okay, it is covered. We need to cover that. Okay, let's keep going because we still have time. Negative binomial random variable. Suppose the independent trials, each having probability, same setup, being a success, are performed until a total of R successes is accumulated. Okay, so here we consider R successes already happened. If we let X equal the number of trials required, then you know, N trials required to enable to have R successes. So that is out of N minus 1, choose R minus 1 is a success. We have R successes. We have 1 minus P. We have N minus R failures. All right, so out of N minus 1, choose R minus 1. Because we don't consider the Nth one, right? Choose R minus 1. N equals to bigger than R. So this equation, in order for the rth success to occur at the nth trial, right? There must be r-1 successes in the first n-1 trials, and the nth trial must be a success. So that's a setup. So this is not so difficult to understand, right? So in the previous n-1 trials, we need to have r-1 successes. And the number nth trial is a success. It's an rth success. So comparing to geometric, let's not compare, right? Just remember it is this. So this one is just consider out of R successes. You know, we need to reach R successes. So it is a probability distribution because we can do this calculation. So this calculation, if we calculate this is 1. Okay, try to convince yourself. I'm not going to go over this. Let's see an example. If independent trials each result in a success with probability P are performed, what is the probability of R successes occurring before S failures? Before S failures. The solution will be arrived at by noting that R successes will occur before S failures if and only if R successes occurs no later than R plus S minus 1 trials. Why minus 1? Oh, because same thing, right? The nth one, the last one is a success. This follows because R success occurred before or at this trial. Okay, so this is the case, right? This is what I was considering. Then it must have occurred before the S failure, and conversely. Hence, from the equation, previous equation, we have this. So we just start n equals to R, right? At the nth trial is a rth success. Then up to R plus S minus 1, because remember we have R minus 1 successes already before this success. Before reach this R success, we have R plus 1, R minus 1. But then we have to have S failures. So this makes sense, right? This is intuitive, R plus S minus 1. And then this is the same thing, out of n minus 1. We have out of n minus 1 trials, we have R minus 1 successes. Then R successes, 1 minus P, n minus R failures. Right. So this is a little bit different. Is, you know, we have S failures before accumulating these R successes. The difference is just this. Okay, let's see a real example. Hopefully, this is a real example. The Banach match problem. At all times, a pipe-smoking mathematician carries 2 matchboxes, one in his left-hand pocket and one in his right-hand pocket. Each time he needs a match, he's equally likely to take it from either pocket. Consider the moment when the mathematician first discovers that one of his matchboxes is empty. If it is assumed that both matchboxes initially contained n matches, what is the probability that, so each one contains n. So what is the probability that there are exactly k matches in the other box? K starts from 0 up to n. Okay. Let E denote the event that the mathematician first discovers that the right-hand matchbox is empty. So, okay, E denote that right-hand matchbox is empty. And that there are k matches in the left-hand box at that time. Now, this event will occur if only if the n+1 choice of the right-hand matchbox is made at the n+1 plus n minus k, right? So right hand and left hand trials. Hence, from the equation, what do we have? Well, P probability equals half because from either box, right? We only have two boxes. And success R equals n+1. And then little n equals to n plus n 2n minus k plus 1. Then probability of such equals to n plus 1 minus 1, which is n. Then probability, because in here we have p equals a half and 1 minus p. We have p equals a half and 1 minus p also equals a half. Right? So we have, so this is already combined together. So we have n plus 1, 2. So we have 2n minus k plus 1. Okay, so there is an equal probability that is the left-hand box that's first discovered to be empty, and there are k matches in the right-hand box at the time. So the desired result is 2 times the probability equals to, right? So times 2 times 2. So 2 times half, that's 1. That's 1. This plus 1 disappeared. So we get this nice stuff. Out of 2n minus k, choose n, half raised by 2n minus k. This is interesting. This is a classic question. Let's say AF. Compute the expected value and the variance of a negative binomial random variable with parameters R and P. Right? R success, probability of success. So random variable raised by k. The value of random variable raised by k. Well, just follow that. Follow this probability distribution and do the calculation. Oh, okay. So we'll borrow the 1n for this. So that's what n minus 1, out of n minus 1, choose r minus 1 becomes out of n choose r. Then p, so we did a 1 over p, and the 1r comes here, 1 over p raised by r plus 1, then 1 minus p, and minus r. Right, so we use these combinatorial effects. Then, where does m come from? Oh, the dummy variable. So now we just let m equals to r plus 1. So we'll start from the next one. N equals to r. So m equals to r plus 1. Basically, m equals n plus 1. So now m equals n plus 1, n equals m minus 1. So all the n's becomes m minus 1. All the n's become m minus 1. Then this is p raised by r plus 1 minus p m minus 1. So this whole thing is the formula. Then adds up, so this should be 1. Summation of this part should be 1. But we have this m minus 1 raised by k minus 1. M minus 1 raised by k minus 1. Oh, okay. So this is the term where the number of the trials, and this is the probability. So that's why we get expected value of y minus 1. So y is a negative binomial random variable with parameter r plus 1 and p. All right, so that's y. What does y represent? Y represents a negative binomial random variable. I wonder why it called a negative binomial random variable with parameter r plus 1 and p. So setting k equals to 1, we have this k, right? We have this x raised by k. Well, x raised by 1, that is the expected value. So the expected value is just r over p. R over p. R is accumulated success, p is the probability. Setting k equals to 2, that's expected value. So we want to calculate the variance. Expected value of the random variable square is r over p, because it's this, right? Y minus 1, 2 minus 1, 2 minus 1 just raised by 1, so it's e y minus 1. Well, what's y minus 1? Y minus 1 has this r plus 1 and p. So it's just r plus 1 over p minus 1. Then do the calculation. So variance equals to this ex squared minus e of x squared. And what do we get? We got r times 1 minus p over p squared. All right. So that's the variance. So expected value is r over p. Variance is r times q. If you want to remember that as q, or just r times 1 minus p, the probability of the failure, divided by p squared. Okay, let's see this one. Let's see this example. Find the expected value and the variance of the number of times one must throw a die until the outcome 1 has occurred 4 times. All right. Since the random variable of interest is a negative binomial with parameters r equals 4, p equals 1 over 6, because getting 1 from tossing a die is 1 over 6. So we have this expected value equals to 24. R over 1 over 6, right? 4 over 1 over 6 is 4 times 6, which is 24. And the variance is R times 1 minus P, which is 5 over 6, divided by 1 over 6 squared. Do the calculation is 120. Interesting, huh? What is this? Now let's see. Let's read this. Now let us suppose that the independent trials are not ended when there have been a total of r successes, but that they continue on. Aside from x, the number of trials until there have been r successes, some other random variable of interest r for s greater than 0. The number of trials until there have been s failures, which we did. The number of trials until there have been either r successes or s failures. Interesting. The number of trials until there have been both at least r successes and at least s failures, because each trial is independently a failure with a probability of 1 minus p. It follows that y is a negative binomial random variable with probability mass function. Okay. Okay, this is for y. This is for this. This we already know. Let's see this. To determine the probability mass function of v equals minimum of x and y, note that the possible values of v are all less than r plus s. This is for the second situation. The second situation is either R successes or S failures. So consider both. Then the third one is Z. Z is at least R successes and at least S failures. I see. Okay. All right. So that's all. And for today, anyone has any questions? Okay. If no questions, you are free bird. Go ahead and do your. Yes.
Oh, you're not gonna talk about 4.83?
4 point what?
4 point the one with hypergeometric.
Oh, I don't think a hypergeometric is on the syllabus. Let's see. Let me see. Hypergeometric. Let me show you the syllabus. Let me share with you. Oh no, I'm still sharing this with you. I'm supposed to share with you the syllabus. Can you see the syllabus? Oh no. Oh, hold on. Someone's having some comments. Okay, I see. So we are done for chapter 4, right? I think so. Hold on. Are the midterm questions going to be more like the homework or like the sample tests you uploaded on Blackboard? More like homework and examples on the chapter in the chapters. We'll study both. Actually, yeah, more like the homework. More like homework and examples on the textbook. The examples I talk about in class. The exams, the previous exams just give you a little bit of idea before semester, you know, what's going on in this class. You're welcome. You're welcome. But lots of questions to go over. Would you narrow it down? Just study. Let's see this syllabus. So what have we studied? We didn't really do the first one, right? Because I just think you understand this. We didn't do that. We had some combinatorial analysis, right? Combination, permutation, multinomial coefficients questions, conditional probability, apply Bayes formula, of course. Calculating some variance, expected values. Bernoulli, binomial random variables, Poisson random variables, geometric and negative random variables. I'm not even sure. I may not have geometric or negative binomial random variables, especially negative binomial random variable. I don't think I have that question, but this will appear on your final exam. If nothing appears in this exam, will appear in your final exam. Yeah, because you have, if you have been doing your homework, you know, if you have been following along with me in class, you shouldn't have any problem for this exam. 12 questions. Okay, any other question?
Professor?
Yeah.
Can you go back to like 4.8.1?
8.1, okay, I will. Eight 4.8.1. 4.8.1. Yeah.
Can you go to like, I think it was like the example C? Was
Examples AC, right?
Yeah.
This one? Calculating the variance.
Yeah.
Okay.
Go down a little bit.
This.
I was confused with one part where like,
yeah,
you know how like in there this q expected value x squared plus 2q expected value x plus 1.
This one?
No, the one like on top of like using expected value x. No, the other one.
This one?
Yeah, that's that one.
Oh, okay.
Yeah.
How do we get from here? From this one to this?
The question is, I don't know where the q expected value squared went.
Q is 1 minus P. Oh, Q, right? Okay. Remember what is the what's the formula for geometric distribution? It's Q raised by J minus 1. Remember, until we reach R success, we have to have R minus 1 failure. Here. Here. We have to have N minus 1 failure. So the formula has to have J minus 1. So that's why, so this Q, we're splitting into Q and Q raised by J minus 1. And J minus 1 into the calculation of this expected value of random square.
Yeah, I understand that part, but when
which part?
Onto the next step.
This one?
No, the one with the Q expected value x. Yeah, it applies to that, right?
Okay, hold on 1 second. You mean how do we get from here to? Okay, look at this. We have expected value of random square. We have Q times random expected value of random square.
That part.
We move this to the left. We move this one to the left-hand side. Do you see? We factor out expected value of random square, then multiply by 1 minus Q.
Yeah.
So what's 1 minus Q? P.
Yeah. Oh. Because I was confused. Where did the Q go? Like.
because we have one here, so 1 minus Q becomes P.
Oh, 1 minus Q is P.
Yeah.
Because I was confused where it went. That's right.
Because this is too far away. Because 1 is here.
Okay.
Okay. Any other questions?
That's good.
Okay. Anybody else has any questions? I really like this class. I think this class is really fun. I think I have learned a lot from you guys. Okay, keep preparing yourself, doing your homework, prepare yourself to present next class, all right? And that's it for today. Oh, next class is our exam, isn't it? Oh, yes, let's talk about the exam. Let's talk about the exam. All right, let me share my, let me reshare my screen with you. Yeah, so the exam should be easy for you. All right, if you go to assignments, you go down, so you have a homework to upload. You will see midterm March 21st, 2023. It's not available now. It's hidden from you, but it will be available March 21st, 2023, 6:05 p.m. All right. It'll be open, and once you finish, you do the same thing as you upload or submit your homework. All right. If you do have a problem to upload, send to my email. I should write here. Let me write here. Edit. Okay. Oh, hold on. This does not allow me to do that. Okay, so how much time I give to you? I give you 20 more minutes to take pictures to upload. All right, so it starts from 6:05, ends at 8:25. Any questions? I will get online on 6, so 5 minutes early. Or if I could, maybe I'll get online early that day. So if you have any questions, you can still ask. What is chapter 4 home? When is chapter 4 homework due? Let's see. Do we join class while we take it? You don't have to. Once you know what to do, you could just go ahead to start your exam. So homework 4, when is it due? May 1st, chapter 4, May 1st. Oh, I haven't changed it. I need to change this. That's too far away. Let me change this. Because at the beginning of the semester, I just do randomly. Homework 4. Edit. So we'll do, let's see, 23rd would be nice. Okay, all right, let's do 23rd. April 23rd. Okay, April 25th. All right.
Shouldn't be like in March.
Oh, right. It's March 25th, right? Thank you. Because we're in March, we're not in April. I was confused. So March 25th should be good, right? So after exam, you have, because it'll be a good review. Since now you have to take exam 1, so you need to finish chapter 4, reviewing chapter 4. At the same time, you could do your homework. So by 25th, you should be able to finish and upload. So March 25th, thank you very much. Remind you of that, because we're not in April yet. Okay, that's chapter 4. Okay, chapter 5, I will change it along the way. Let's see. Yeah, we'll change that along the way. All right, so this is meant to be a fun class. Anyone else has any questions?
Wait, so for exam, we don't have to join the class or no?
You don't have to join the class. You do not have to if you know exactly what to do. But ideally, let's just first meet in this classroom, just in case we have anything happen. I remember last semester, we did this, but nobody could see the exam. Something happened. So let's all get on class by 6:05, just in case something happens. If nothing happens, you can just log off from here, from Blackboard, then focus on your exam. Then I will be free that night. I'll just wait for you to submit, then grade your papers. Any other questions? So let's all get on 21st, all right, class time. So we know exactly what to do, and make sure the midterm does open for you. Just sometimes the Blackboard does weird things. Is there partial credits? Always partial credits? Just make sure. You know why I like this kind of class to do presentations? I also like to do like a vector calculus class. I teach, I think Catherine was in the class. Because this advanced class is fun to to present. Because yeah, I think it makes sense. Because when you present, you have to be precise. Sometimes I try to be picky. So then you have to try to be precise. Then also presentation helps you to be neat, right? Because you have to, you're trying to let other people understand your point. So you have to be very clear, very organized, very neat. An exam is the same thing because you are trying to convince me you understand how to do the question. So do that. All right, any other questions? Always partial credits, all right? All right, if not, you are free bird. If you have questions, I'm still here. Thank you. Thank you. Let me stop recording.